Okay, so now that we know how to extract the Fourier coefficients, we can write the Fourier series in a more succinct way using complex numbers. So we can say n goes from minus infinity to plus infinity, and the Fourier coefficients are now Cn and e to the power I. These are the basis function, e to the power I, 2 pi n x over L. And because we are dealing with a real function here, Cn is related to the ans by half an minus I bn for n greater than 0. For n equals to 0, it's half of a0. And for n less than 0, it'll be minus n plus I b minus n for n less than 0. Now, in quantum mechanics, we shall deal with, we shall deal with complex functions, okay? Complex functions, psi of x. And so, for us, Cn and Cn, C minus n, will be independent. Here Cn is equal to, here it's Cn is equal to C star of n, right? So we are not going to do that. Okay. So, so this is the complex form of, and if you want to figure out what Cn is, then we take the integral from minus L to plus L, and we phi of x e to the power minus I 2 pi n x over L d of x, okay? And what we're using here is the fact that e to the power I minus I 2 pi m of x over L e to the power minus I, is it minus or plus? I think minus, yeah. I 2 pi m n of x of by L of d of x minus L by 2 by L by 2, 1 over L. I may get a normalization constant wrong. It's mn. It might be it might be plus here. I'm not sure. Okay. So these are we can use that to derive these things. Okay. So any questions? Okay. So the next question that we want to ask is that how well does the Fourier series approximate our function, right? That's a very valid question to ask, because in reality, when we have an infinite series, but we have a finite computer, we cannot really sum the whole series. So sometimes we can program a computer and which can say, take into account 1,000, 1,000 terms, but not really the whole series. So we need to have a measure of how well our series approximates the function. Now, there can be many different measures, right? But the measure that we are going to use is kind of the a kind of a least square, a least square method. So let's introduce the partial sum. So partial sum, let's call it S of n. N is in an integer, and what it does is that it just, has sums from minus n to plus n with some coefficients dn. We don't know what these coefficients are, but uses the same basis function, 2 pi I n of x over L. So this is a partial sum, but of course the sum is not over all of n. So dn are some constants. Okay? We need to be determined. So the error, is a average, is a mean error is define it to be phi of x minus s of n squared of dx. So this error measures how accurately this partial sum approximates our function. So we can expand this now. If we expand this, we find 3 terms. Actually, 4 terms. And so I'm not going to bother about the x dependence anymore, like not write it explicitly. Okay, is that okay?
So why do we have 2 terms in conjugate instead of 2ab?
Because it's a modulus, not squared.
মডুলাস কার হচ্ছে যে কনজুগেট আর ওটার গুণফল।
Right. This is a plus b, sorry, a minus b times a star minus b star, right? And then we have a squared, and then ab star minus ba star plus b mod squared. Okay, that's what we're doing. So here's 2. So these are not, if they were real, they would add up, but they're not real.
Okay, got it.
All right, good. So, okay, so then what we do is that we use this fact, and we do, these integrals. We do these, the 3 integrals, this one, and this one. Then we get En is minus L by 2 plus L by 2 phi of x squared d of x, and the other ones become sums now. So the sum from minus n to plus n, and then here we have L dn star c of n plus L dn cn star. Remember, L is a real number. And then minus L dn star dn. Okay, so this is what we get after doing the integrations. And then, we can just like do a little bit of massaging of this term, of this expression. And the first term you don't change. And then we get minus n, a sum over from minus n to plus n of L Cn squared. So we're completing the square. This term wasn't there, but we're introducing it so that we can complete the square, and then the terms become L times dn minus Cn squared. Okay, so if you expand this, you will cancel out this one with the extra term that we introduced. Okay, so this is En, and now we can ask, when is En minimized? For what values of D? Of course, I mean, these guys don't depend on D. So only this term, we can minimize this term because it's a positive definite term. And if we can minimize this term, then En would be minimized. And of course, it's obvious that the choice dn equals to Cn will minimize the error, right? All right. Now, originally, the way we defined En, if we go back, it was a positive definite quantity, right? This is, the integrand is positive definite. So it's a positive definite quantity. So En is greater than or equal to 0. So now, because this thing is positive definite, we can then conclude that 1 over L minus L by 2 to plus L by 2 phi of x squared d of x is greater than or equal to, the sum goes from minus n to plus n of Cn squared. Okay? So this sum, the sum is bounded from above, by this number, which is by definition finite, because we're dealing with L2 functions, right? Oh, it's also a function which, and we are integrating over a finite interval. So that means that the limit n goes to infinity of the of the series of this sum, this thing converges to some value, and therefore we can write as a consequence of this the equation where now the integral and now the sum goes from minus infinity to plus infinity Cn squared. Okay, so this is an identity we can write. And it's an important identity called Bessel's identity. Okay,